to sum. This is often called the hello world of the let code. It's simple, but mastering its optimal solution is key to understand the power of hash maps, a tool you will use constantly in coding interviews. We are given an array of integers nums and a target integer target. We need to return indices of the two numbers that add up to the target. Exactly one solution exists, cannot use the same element twice. We are looking for two numbers that num to a target instead of brute force. The brute force way is to check every single pair of numbers that takes log or n square. We'll use a hash map to store and look up complements. Let's walk through an example before coding. Numbers 2, 7, 11 and 15 and target is equal 9. We start with an empty hash map. Index at 0. Number is equal 2. Complement is equal target minus. Number is equal 7. And 7 is in the map, not in the map. So, store number with its index. At index 1, number is equal 7. Complement is equal target minus number is equal 2. 2 is in the map, we found it. It's in the map, return index of the 2 and index of the 7. We only need one pass. Hashmap helps us look up the complement in constant time. Let's check the code together. We will keep number as an integer and we will keep the index of the number as an integer also. We will loop up numbers and for each number we will calculate the complements. We need to check map is included our complements. If it's not, we will put the number and numbers index to our map. If the map is already included complement, return the complement number index and the current index also. Outside of the loop, we need to describe another return and it will be empty array. We only scan the array once or n time. We use a hash map to store previous number or n space. It's one pass hash map trick and it comes up all the time in interviews. Next question is group anagrams. It's frequently asked at Amazon and it's still Amazon favorite. The task is simple and it's very short and your job is to group the words that are anagrams of each other. For example, it, t and 8. All belongs to the same group. Same letters, different order. Grouped based on the character content. Two anagrams will result in the same sorted character string. We can use the sorted word as a key. Group all words by that key using a hash map. Let's walk through a simple example before we jump to code. Sorting each word gives it for 8, t for 8 and so on. When we group by these keys depends on sorted key, et and 8 under aet, and 10 and net under ant, and bet is under abt. That is the structure we'll build in the code. Let's check the code together. We have a string array and we are creating a map, string and list of string. String is for sorted key and list of string is for the list of the words under this key. We are loop up all the string elements. We need to return each word to character string, then we are sorting our characters. When we return this sorted character to string again, this is our key. And compute if absent method is really useful. Here we say with this method, if key is not in the map, we will create a new array list. Key is already in the map or it's not in the map, every time we will add the string to our key. When we get it word and we will return it to character array, then we will sort it to aet and we will return it to string again. For it, the key will be aet. So we don't add it before our map is empty. It will add the key with an empty array list. Then we will add 8 to our list. For the second word, we will return it to array list again. We will sort it to aet. And when we return it to string, our key is aet string. When we come compute if absent method, yes, we have the key before, so we don't need to create a new array list. We need to add the word to the list. We will return the values of the map as a result. Sorting each string takes key log key, where key is average word length. For n words, Total time complexity is n multiply key log key. Space complexity is O n key for sorting group strings. This is a classic problem using hash map and it shows up in many variations. Next up is subarray sum equal key, one of Amazon's top ask prefix sum hash map problem. The goal is this. You are given an array of integers, numbers, and an integer key. Your task is to find the total number of continuous subarray whose elements sum up to exactly key. We'll use prefix sum pattern. Instead of summing every subarray, we track the running sum and look back to see if there is a subarray ending here that sums to key. To do this, we use a hash map to store prefix sum and their counts. Let's check an example together. Our numbers array is 3, 4, minus 2, 2, 5, and 7. And the target key is 7. When we check the subarray sums, 3 and 4, the sum is equal 7. 3, 4, minus 2, and 2, sum is equal 7 also. And 2 and 5, it's equal 7 and 7. Let's trace this with a realistic example to see how powerful this concept is. Sum is our odometer, and our map is a log of all the distance we are past. We start our journey, our sum is equal 0, and the count is equal 0. And our map is visited locations start with 0 kilometer 1 time. To handle subarrays that starts from the very beginning, we'll go number by number to see exactly how the logic works. We encounter our first number 3. Our sum becomes 0 plus 3 is equal 3. We ask, have we seen sum minus key, which is 3 minus 7 is equal minus 4 before? We check the map, so no, count remains 0. We update our map with our current location and we will add 3 kilometer we passed there 1 time. 3, 1. Next up is equal 4. Our sum becomes 3 plus 4 is equal 7. We ask, have we seen sum minus key, which is 7 minus 7 is equal 0 before? We check the map, yes. We have seen sum of 0 1 time. This means we found one new subarray, 3 and 1. We update our counter, count is equal 0 plus 1 is equal 1. We update our map, we add and we see the 7th kilometer 1 time, 7, 1. Next is minus 2. Our sum became 7 plus minus 2 is equal 5. We ask, have you seen sum minus key, which is 5 minus 7 is equal minus 2 before? We check the map, no. Count remains 1. We update our map because we passed the 5th kilometer 1 time and we will add 5th and 1 in our map. Next is equal 2. Our sum becomes 5 plus 2 is equal 7. We ask, have we seen a sum of sum minus key, which is 7 minus 7 equals 0 before? We check the map. Yes, we have seen a sum of 0 1 time. That means we found a new subarray, 3, 4, minus 2, 2. We update our counter, counter is equal 2. So we update our map, we have seen the sum 7 for a second time. Next up is equal 5. Our sum becomes 7 plus 5 is equal 11. We ask, have we seen a sum of sum minus key, 12 minus 7 is equal 5 before? We check the map, yes. We have seen a sum of 5 1 time. We found one new subarray, 2 and 5. We update our counter, 2 plus 1 is equal 3. We update our map, we need to add 12 kilometer and we come here the first time, 12 and 1. Our final number is equal 7. Our sum becomes 12 plus 7 is equal 19. We ask sum minus key. 19 minus 7 is equal to 12 before? We check the map. Yes, we have seen a sum of 12 1 time. We found one new subarray 7. We update our counter. Counter is equal 3 plus 1 is equal 4. We update our map. We need to add 19 kilometer 1 time. We passed here the first time. And we have reached the end of the array. Our final counter is equal 4, which is the correct number of subarrays. By checking at every single step, we can be sure we haven't missed anything. Check the code together. We define counter and sum is equal 0, and we define a hash map to store the frequencies of prefix sums. To put 0 and 1 to prefix sum is the most critical line. It's our base case. It ensures that if the running sum itself equals key, we count it as a valid subarray because key minus key is equal 0. Sum is equal sum plus number. At each step, we update our running total. Counter is equal counter plus prefix sum, get or default 0. This is the core logic. We check the map for the sum minus key k. If it exists, we add its stored frequency to our count. If not, we add 0. After our check, we update the map with the current running sum's frequency. This makes the current sum available for future steps. We only make a single pass throughout the input array. This means the time complexity is linear, or ON. In the worst case scenario, all the prefix sum could be unique, requiring us to store all of it in the hash map. Therefore, the space complexity is also ON. For our next problem, we are taking a question that's a favorite in Amazon interviews because it tests your knowledge of two most essential data structures, hash map and heaps. The problem is top key frequent element. The code is very simple. You are given a list of numbers and an integer key. You need to find key numbers that appears most often in the list. Let's trace this with an example. Numbers is equal 1, 1, 1, 2, 2, and 3. And if we create a map and check the frequency of the elements, first integer key is for the number and the value integer for the frequency. So, when we check all the each elements of numbers, 1 seems 3 times, 2 seems 2 times, and 3 seems 1 times. We need to return 1 and 2 most frequency elements. The optimal solution is a clean two-step process. Step 1, count frequencies. We need to know how many times each number appears. We'll build a map of each number to its frequency. Step 2, find the top key. Once we have our counts, we need an efficient way to find the key elements with the highest frequencies. While you could sort all the unique elements by frequency, a more optimized data structure for any top key numbers is a heap, which is called a priority queue in Java. Especially, we'll use a min-heap of size key. We'll iterate our numbers. For each one, we add it to heap. If the heap sizes ever grows larger than key, we will simplify, kick out the smallest element, which is in our case is the element with the lowest frequency. Heap will contain exactly top key, most frequent elements. Next up, we have a fundamental string and array problem, valid anagram. This is another frequent class question that tests your understanding of character manipulation and frequency counting. The problem is this. Given two strings, S and T, determine if T is an anagram of S. An anagram is a word formed by rearranging the letters of another, like listen and silence. Two strings are anagrams if and only if they have the exact same count of each character. While you could sort both strings and compare them. That's less optimal at ON log n. A more efficient ON approach is to use a frequency map. Since we are often dealing with lowercase English letters, a simple array of size 26 is the perfect and most efficient tool for the job. Let's check the code together. This is the simple but critical optimization. If the lengths are different, they can't possibly be an anagram. We create an integer array to act as our frequency map for all 26 lowercase English letters. For each character in S, we find its position in the alphabet. For example, for B, the position will be 1. To calculate this, we always check character minus A. B minus A is always 1. And increment the counter at that position. At the same time, we do the opposite for the character in T. Decrement the counter. If the strings are perfect anagrams, every increment will be perfectly cancelled out by a decrement. If any count is not 0 at the end, it means that's a mismatch. We iterate through the string just once. It means the time complexity is O(n), where n is the length of the strings. We use an array of fixed size 26. Since this size doesn't change, no matter how long time input strings are, the space complexity is constant, O(1). This is a very important detail to mention in an interview. Alright, it's a time to level up with a problem that's a true test of your algorithmic things. Minimum window subarray. It's a classic question frequently seen in interviews at Amazon and other top tech companies because it requires a dynamic and efficient approach. The problem is this. You are given two strings, a long source string S and a shorter target string T. Your goal is to find the smallest possible substring within S that contains all the characters from T, including duplicates. The optimal solution for this is the sliding window pattern. To make it super clear, let's think of it like a shopping trip. The long string is the supermarket aisle. The target string T is our shopping list. Our window is our shopping cart. The algorithm has two phases that we repeat. First, we push our cart down the aisle, move the right pointer, adding every item we see. We have a counter to track how many items from our shopping list we have fulfilled. We keep extending until that counter tells us our list is complete. Second is contract phase. The moment our list is complete, we stop. We have found a valid but maybe too long shopping trip. Now we try to find a shorter path. We move from the start of our trip, the left pointer, and put item back on the shelf one by one. As long as our shopping list remains complete, our trip gets shorter, and we update our best record. The moment we put back an essential item that makes our list incomplete, we must stop contracting. With an incomplete list, we go back to the expand phase to find the missing item again. This expand contract cycle is the entire logic. Let's trace this visually. We have a string S and a string T. We need to find A, B, C. Our need count is 3. Our right pointer expands. It finds A, then a B, and finally a C. Our window becomes ADOBEC. It's our first valid window. The length is 6. This is our current best answer. Now we try to shrink. We remove A from the left. Our window is now, it's no longer valid because we need an A. So we must stop shrink. With our window invalid, we must extend again. Our right pointer continues moving and then it finds another E. Our window is now, it's valid again. The length is 10, which is not better than 6. We try to shrink it. We remove our window till C. Bank B, A, and C was better. B, A, and C is the final answer. The algorithm continues this expand and contract process, but won't find anything shorter. That's our result. Let's check the code together. If S is null, T is null, and S length less than T length, return an empty string. Then initialize left and right is 0, start is 0, minimum length is equal maximum integer, and required size is equal T length. Need is our actual shopping list. A hash map tells us how many of each character we need to find. We extend our window. We grab the character C at that position. We check if this character is on our shopping list. Need contains key C. If it is, we check if we still need it. If we do, that's great. We found one of the items we are looking for, so we decrement our required counter. We then update our shopping list to say we need one less of that character. If we find more than we need, this count can go negative, and that's okay. Finally, they expand our window by increment right, which means our shopping list is complete and we have a valid window. Now our goal is to make this window as small as possible. First, we check if our current window is a new record holder for the shortest length. If it is, we save its start position and min length. We get the character from the left side of the window, the one we are about to remove. We check if this character we are removing was on our original shopping list. If it was, we return it to the list by increasing its count in our neat map. This is most crucial part. After returning the character, if its needed count goes above 0, it means we just lost an essential character that we need. Our shopping list is now incomplete, so we increment required. This will break us out of this inner while loop and send us back to the expansion phase to find our missing character again. Finally, we shrink our window from the left. At the very end, we check if we ever found a valid window. If minlen was never updated, we return an empty string. Otherwise, we use start and minlen of the base window we found to cut out and return our final answer. Each pointer left and right only moves forward through the string as once. This gives us a linear time or n time complexity, where it is the length of s. We can call space complexity or m, where it is the number of unique characters in the target string t. Another essential interview question that perfectly demonstrated the power and elegance of the sliding window pattern. Longest substring without repeating characters. The goal is simple to understand but requires a clear solution. Given a string like ABC, ABC, BB, you need to find the length of the longest string that does not contain any repeating characters. For our example, the answer is ABC, which has a length of 3. Once again, checking every single possible substring would be far too slow. The optimal solution is a dynamic and efficient sliding window. Our tool for this problem will be 2 pointers left and right to define our window and a hash set. The hash set is the key. It will store the characters currently inside our window and allow us to check for duplicate in constant time. Let's trace with a great example. We start with our right pointer at index 0. The character is A. A is not our set. We edit and update our maximum length. Next B. It is new and edit and update maximum length to 2. Next C. And it's new, edit, and update maximum length to 3. Our window is now ABC. Now our right pointer move to the next character, which is A index 3. We check our set. Does it contain A? Yes, we have a duplicate. We cannot expand our window anymore. To fix this, we must shrink our window from left until the old A is gone. We look our left pointer at index 0, character A. We remove it from set and move left one step to the right. Character set is equal BC, left is equal 1. Now the duplicate A is gone from our set. With the conflict resolved, we can now add a new A. The current window is BC. A, the length is 3, maximum length is still 3. Our right pointer moves to the next character B. Duplicate. Our set already has a B. So we shrink from the left again. Remove left, which is B, and left becomes 2. Now we can add the new B, it's the right one. Current window CAB length is 3, maximum length is still 3. The process continues like this with the window sliding along the slides, expanding when it finds unique character and contracting when it hits a duplicate. Throughout this entire problem, the longest valid window we ever found had a length of 3. And that's our final answer. Let's check the code together. First, we set up our tools, create a hash set called window, and left is 0, maximum length is 0. We started the expand window from 0 with right pointer, it's equals 0. Get the current right character. If window contains the current character, we will shrink the window. And we will remove left character till window doesn't contain current character. Once we are sure our window is valid, we add the current character to our set. Then we calculate the size of our current valid window, which is right minus left plus 1. We compare this size with our maximum lag. After the for loop has finished, our maximum lag variable will hold the final answer and we simplify return it. Efficiency of the sliding window pattern. Even though we have a nested while loop, this is not O(n) square. Each character in the string is visited at most twice, once by the right pointer and once by the left pointer. This means the time complexity is linear, O(n). For space complexity, the worst case, all characters in the string are unique, and our hash map will group the size of the string. The space complexity is O(n). Classic of algorithm interviews, maximum subarray. This problem is famous because its solution, Kadanes algorithm. It's incredibly simple, clever, and efficient. The problem is this: you are given an array of integer which can include both positive and negative numbers. Your job is to find the continuous subarray that has the largest possible sum and return that sum. For example, in the array -2, 1, -3, 4, -1, 2, 1, -5, 4. The maximum subarray is 4, -1, 2, 1 with a sum of 6. The logic is is incredibly simple. Think of it like this. You have two values you are tracking. One is your current sum. This is the sum of the subarray you are building right now. The other is your maximum sum. This is your all-time record. As you walk throughout the array, we add each number to your current sum. But here is the one rule you need to remember. If your current sum ever becomes negative, it's a dead weight. Drop it, restart it to 0, and start building a new subarray from the next number. At every step, you simply compare your current sum to your maximum sum record and keep whichever is bigger. That's it. One test, one simple rule. Let's check the code together. Max will be our all-time record holder, the biggest sum we found anywhere in the array. Current sum is the number of the subarray we are currently building. We initialize both of them with the very first number in the array. Then we started loop from the second element of the array and walk through it one number at a time. This is the heart of the entire algorithm. At each new number, we make a simple but powerful decision. It's better to expand our current subarray by adding a new number, current sum plus numbers e, or it's better to discard our old subarray and start a brand new one with just the current number c. MathMax Simplify picks the perfect of these two options for us. This ensures our current sum is always the maximum possible sum for a subarray ending an exact position. After we figured the best possible sum ending at our current spot, we compare it to our all-time record max. If our current sum is bigger, we have a new champion. We update max. After the loop is finished, our max variable is hold the largest subarray and we will return it. It's a beautiful O(n) solution. We iterate throughout the input array exactly once. Constant time operation at each step. This gives us fast time complexity of O(n). We only use a couple of variables to keep track of our sums and we don't use any extra data structure that grow with the input size. This means the space complexity is constant O(1). Alright, next up is a problem I already love because I think it was the first medium problem that I truly understood when I was first learning. Container with most water. It's a classic two-pointer problem that looks tricky at first, but has a beautiful intuitive solution. The problem is this: you are given an array of non-negative integer representing vertical lines. Your goal is to find two of this line that can trap the most water between them. To find a potentially better container, we had to move one of the pointer inward. Which one? The golden rule: we always move the pointer of the shorter line. The amount of the water is always limited by the height of the shorter of the two lines. If we move the taller line's pointer inward, our weight gets smaller, but our height is still limited by that same short line. The area can only get smaller or stay the same. But if we move the shorter line's pointer, we take a change. Alright, let's trace our algorithm with the classic example. We'll keep track of our pointer and maximum area we have found. We start at the left at index 0, right at index 8. The distance between left and right is equal 7. The height is limited by the shorter bar. The area is 8 multiply 1 is equal 8. Maximum area is now 8. The left line is shorter, so we move it. Now left is at index 1. Right is at index 8. The width is 7. The height is limited by the shorter bar, which is 7. The area is 7 multiplied 7 is equal 49. Maximum area is now 49, a huge improvement. This time the right line is shorter, so we move right. Now left is equal 1, right is equal 7. The width is 6. The height is limited by the shorter bar, 3. The area is 6 multiplied 3 is equal 80. This is not bigger than 49, so maximum area remains 49. The right line is shorter, so we move to right. Left is at index 1, right is at 6. The width is 5. The height is limited by the shorter bar. Well, they are equal, so height is equal 8. The area is 5 multiply 8, still not bigger than 49. Maximum area remains 49. Since the heights are equal, we can move either pointer. Let's move right. As the process continues like this, the pointer move closer and closer. Always discard the shorter line and recalculate the area. So we saw our maximum area is 49, was found early, and no other combination was able to beat it. When the pointers finally meet, the loop ends and our final answer is 49. We define our tools. Max area is equal 0, left is equal 0, right is equal end of the array. Our loop continues as long as our pointers haven't crossed. Calculate the width of the container. Calculate the height is limited by the shorter of the two lines. Calculate the area of the current container. Update the maximum area found so far. Move the pointer of the shorter line inward and return maximum area. The left and the right pointers start at the ends and move toward each other. Each pointer will only traverse the array once. This gives us a single path solution with a beautiful time complexity of O(n). We only use a few variables to store our pointers and the maximum area. Therefore, the space complexity is constant O(1). Let's tackle another interview staple that you might see in problems related to calendar scheduling or data consolidation. Merge intervals. You are given a collection of intervals, where each interval has a start and end time. Your task is to merge any intervals that overlap and return a new list of clean, non-overlapping intervals. For example, 1, 4 and 3, 7 overlap and should be merged into a single interval, 1, 7. The secret of this problem is to stop thinking about code and start thinking about your daily calendar. You have a messy list of meetings. What is the first thing you do to make sense of it? Step 1. You sort them by their start time. This instantly bringing order to the chaos. Step 2. You merge them. You go down your sorted schedule. If the next meeting starts before your current meeting's block ends, they overlap. You simply extend your current block to cover both by taking the latest end time. If it doesn't overlap, it's a new separate meeting block. That is the entire algorithm. Sort and merge. It's that simple. Now let's see it in the code. We sort the intervals based on their start times, the first element index 0. This allows us to make a simple greedy choose at each step. We ask two things: if our result is empty, or is the end of our last merge interval before the start of current interval. If either is true, there is no overlap. If there is one overlap, we simply add the current interval to our result list. There is one overlap, we don't add any interval. Instead, we just update the end of the last interval in our list. We set its new end time to be the maximum of its old end time and the current interval's end time. The performance of this algorithm is dominated by the initial sorting step. Sorting an interval takes O(n) log n time. After that, we have a single loop throughout the intervals, which is O(n). Therefore, the total time complexity is O(n) log n. For space, we are creating a new line to store the merge intervals. In the worst case, if no interval overlap, we will store all n intervals. The space required for the answer is O(n). We are coming off the end of our first 10 questions. In the next video, we will solve another 10 problems with the same patterns. These questions are not popular just for Amazon. They already ask of another company's interviews. If you watch this video to the end, you are lucky. And good luck during your interviews. Don't forget to like, subscribe and give a comment. See you in the next one.